Today we are going to see how CAMG, which stands for Computer Aided Modeling Program, actually derive the equations automatically. So that's why I entitled this Computer Generated Differential Equations. So what you have on the screen is basically a simple system in here, the bond graph of which is on the right hand side. Just to review very quickly what we have this reference, the wall in here. We model it as a source of velocity 0 just so that we have a reference, and then the other velocity of the mass is over here. So we follow the regular established procedure that we have indicated in previous videos, and that how we actually generate this bond graph model by attaching all the elements on the one junctions, and then we use zero junctions to produce the velocity differences and attach the elements that see or experience those differences, and that way we have come up with this bond graph model. Now, in the previous lecture, what we had done is derive all the equations by following this procedure. We write the constitutive equations for each one of the elements, and then we came up with a set of individual equations. How do we do this? See, we started from the beginning here. We said, okay, look, you have like E1 is equal to E2 following the causal marks, and F1 is SF1, and for each one of these we put the constitutive law following the power flow and the causal marks. It turns out that when we do that, we have this C element producing this derivative in here, and the I element producing this other derivative. So in reality, the system of equations that we have is in here we have let's see, hold on for a second. We put the system of equations that we have consists of this set of equations like this are the entire set of equations that correspond to this bond graph model. But you see, in here we have individual equations and the derivatives, but in fact what we have are basically two derivative equations that have all these other components that together they make up these two equations. So what we did, we said we're going to simplify this, although this is perfectly okay for computer simulation. In fact, CAMG and MATLAB have no problem in doing this, and in fact these equations are better if you have nonlinear systems, because you can basically modify any of them. And in here we reduce it to two expressions by substituting, like dq4 dt was f sub 4, and then f4 was f sub 3, and then we had this f sub 3 is f6 minus f2, and so on. We came up with this expression right here. All right. So if you have this case, I mean that's the equation, and then we had this other equation. But this was a lot of work, and I think is fine so that we understand what bond graphs have behind them. But now we are going to help ourselves using an automated approach to get the computer to do this job for us. So now what we're going to do is I'm going to go back to the notes as begin making today. This is what we have from the previous one. We have the bond graph model, and we have these equations here, these two equations. So what I propose now is let's go and enter this into the CAMG software, and we'll see what it does. So we're gonna go over here and then go to into CAMG, and then click on the model here, and we need to keep the one well, first of all we need to get started. We need to produce a new model here, and so we are going to I'm going to move this a little farther down in here, and I would like to keep the bond graph model here on top or close to in view is what I'm trying to say. Maybe we'll move it in such a way that we only have the bond graph view in one window, and we have CAMG on the other one. So let's just go over here, and we're gonna put it just there in the corner. This way we can see it really well. See? All right. So in here, it really doesn't matter which way you start, but if you just so that this, we can start by putting the one junction here, and then we put the SF over here, so that you have this, and then we put the 0 over here. I'm just translating what I have on paper now. So and at this point it doesn't matter in which order you build this, because we already went through the logistics about how you build this block diagram. So this is number 4. I'm gonna build it with the same numbers, so if I enter it in the sequence that my picture on the left hand side has, CAMG will assign the numbers the way I want them. So in here you have from here to here, and then we have an I element up here, and then would be from here to here, and then we have this SE on the side, which goes from here to here. And I have my picture that I have on the notes that I did by hand onto the computer. Now what's gonna happen is we go to interface, and we said go to the MATLAB interface please, and then the two programs will do a handshake with each other. And what is happening as we are doing this, what will happen is that the CAMG produces the MATLAB input files already an M file. In other words, we do not have to program MATLAB. CAMG is going to extract all the information from our bond graph model and produce an actual usable model in MATLAB, so that we can actually perform simulations. What we are concentrating today is on the ability of the of CAMG to generate these equations automatically. So that's why we title our lecture today Computer Generated Differential Equations, or we could say an automated method to produce the differential equations in the Cauchy form and in the state space form. So now that the two programs interacted with each other and they did a handshake, you see there's the steps over here. It produced a model file which we use for the time domain simulation, and produce a CAMG EQU, which is the equations file, and we have two other files that we will talk later on, but today we'll concentrate on the CAMG module, which is the model file where you find places to initialize your variables and define the time controls. But what's important right now is this one. CAMG EQU is the one that generated the differential equations. So these equations that you see on the board right now, these ones, should be exactly the same as I had them on paper. In fact, I'll go back there and let's see if we can put the equations on the screen so we can see them and compare them. These ones right here, see? Okay. These equations, you see where it says dq support is F4, F4 is F3, like this, and you have F1 is SF1. See this one? Right here is this one, right there, and so on. So all the equations you have, you see it in here. There's a little difference. We went through just the number 1, 2, 3, 4, just for convenience, so you could order any number. CAMG does one more step. It looks at what equations need to be defined first, what variables need to be defined first, and organizes it that way. So it has a logical sort logic inside CAMG as an intelligent feature of the program that tells MATLAB how to compute, but organizes the equations in such a way that MATLAB would have no problem in computing this. But this is just to verify, like dp sub 2 is e sub 7. You're gonna see it right here. Not dp sub 2, dp7 is dp7 is e sub 7. Okay, that's what you see right here. See? So, but CAMG goes beyond this. It says, okay, I am going to produce them also in the Cauchy form as single expressions, and I'm going to use them, produce them also in a state space form. That's something that we have to get used to on how that is done, but it actually comes from this two sets, from these equations. So if you go to here, well, let me put the two expressions as we are talking about. See, these are those two expressions right there. I think we might need a little bit more space. Yeah, there you have both of them. They look good. If you go over here to the CAMG-SYM file, this CAMG-SYM file stands for symbolic file, CAMG-SYM. What it does is it has some places to initialize values, of course, but it has the equations in the Cauchy form. This equation that I just highlighted should be exactly like this one. Take a look at it. Isn't that exactly right? It is. And if you go farther down in here, this equation in here should be exactly like this one on the right hand side. You want to test it? See here, dp7 dt is minus q sub 4 over c sub 4, which it is. The little minus is a little guy here. And then it says SF1R5. SF1R5 is here. And then it has minus P7 over I7 times R5. That's this term. And it has mass plus SE8 right there. Okay. Now you see, I am going to show you what CAMG does beyond this. So these are the Cauchy form of the equations. There are two single expressions that are, they are in simple expressions in there. CAMG says, wait a minute, I am going to use these expressions to produce the so-called state space form that MATLAB is also designed for. So what we're going to do is, besides what we have already massaged these equations into being just two simple expressions, I am going to put them into matrix form. And I want to show you how to do that, okay? So, and I'm also, first I'm going to show you by hand, and then I'm going to show you what CAMG actually does to do that, okay? So the first thing we need to start is that, and you will accept at this point that what CAMG has done, it has automatically derived the equations. The computer went ahead and after having entered the bond graph model, okay, that's all I need. I have these equations. Now let's take a look and concentrate on this idea about the state space form. Okay, so I think we need. I wanted to do it this way. So I am going to start over here, and I am going to use a form that is a format that we call a state space form. Let me first start with the format, what we want to do, and then we are actually going to do it to these equations. You want a form where the derivatives look like a vector in here, and then the state variables are put into a vector and a matrix called the A matrix. And in here we have some matrix like this, and then the inputs are over here. Then finally you have a vector for the outputs. This is the C matrix that we're going to call it, and then the state vector plus the D matrix multiplied by the input vector. This whole thing that you see here is called state space form, or is also called a state variable form. Okay, we would like the equations that we have upstairs in here to be in this form. So what I'm going to do is I am going to say, okay, in order to build this up, to build this vector, I'm going to say that what did we have? dq sub 4 dt is one derivative, right? And then we have the other derivative, that is dp sub 7 dt, right? You see right there we have made this vector. So we have already done this one. Yeah? So now what we're going to do is we need to build the A matrix in here, this one, yeah. And so we're gonna say, okay, equal, and then we're going to put this in here, the vector over here like this, yeah. And then you have this two state variables. You have q sub 4 and you have p sub 7, and then you're gonna say plus this matrix here, and then the state space, I mean the input vector. And here you have two of this. You have SF1 and you have SF8. So right now we need to fill what goes into here. So you see at the top I7 times P sub 7. So if you multiply the row here times this vector, this is going to be a 0, and this is going to be minus 1 over I sub 7. And then this row here is going to be a minus 1. If still you are a little puzzled of what I did, here's what I invite you to do. Multiply this row by this column, multiply this row by this column, and you should obtain this equation. So you see 0 times q sub 4, yeah, it's not there. 1 over I7 times P sub 7, yes, that. And then minus 1 times SF1, that's this. On the bottom one, this one in here for q sub 4 is going to have minus 1 over c sub 4. And then you have this p sub 7, which will be minus r sub 5 over I7. Yeah, and then this other one is gonna have a, okay, this had the SF1, but the SF8 was a 0, so this is going to be SF1 is R5, and then you're gonna have SF8 is, no, SE8, excuse me, and this would be SE8. No, but it's gonna be a 1 in there. Yeah, right here. So this would be SE8 in here. That is here. Okay, very good. What we have done is, do you see what has happened? This is this vector, this matrix is this matrix, this is the state vector, and this one is the output vector. So if maybe if we can use the red color, this guy is the X vector like this. This is the A matrix. This is the vector of state variables. This one is the B matrix, and this one is the U vector. Okay, what I'm trying to tell you is that CAMG did all this for you. This also a state space computer generated form. Now, I don't know exactly whether CAMG put first the q sub 4 variable or the p7 variable. That will remain to be seen when we compute. But I'm just telling you that there's the possibility that CAMG might have reversed the two equations, but it will produce the same matrices. If that's the case, maybe I should do it just for the sake of understanding this. We can. What I'm trying to tell you is that CAMG might have might reverse the order. So I just want you to be prepared that the matrix would be like dp sub 7 dt here, and the other one will be dq sub 4 dt. And you, in that case, you will have the terms would be rearranged a little differently. This would be p sub 7 and q sub 4, and then plus the matrix B here times the other one, the SF1 and SE8, like this. Okay, let's see, and we're going to go ahead and take a look as to what it did, because we are already in here. Yeah, we had those two equations. Do you see this part in here are forming the rows of that matrix? But you may say to me, what do I need to do? Just run the program and you'll see. So we click on run, and where is it? I think we are, there you go. We are seeing the output over here. It's telling you these are the, see the input, the vector in there? Put SF1 of SE8, and it did exactly as I did on paper, Q4 first. This matrix that you see in there, that matrix has to be the same as the one I have. So is the B matrix, the C, and the D we did not specify because we didn't specify any outputs. But let's take a look at the A and the B matrix at this point. So in here we'll go and go back to the notes here. Do you see there's the A matrix? Let's see if we can, if I make it small so we can compare it right there. And let's go over here, and I need to make this too small so you can see. See it right there, the A matrix? 0 and minus 1 over I7, and then minus 1. Do you see what I mean? And then it will go to the B, which is on the, it will be on this side. So let's take a look in here. Do you see the B matrix right here? This one? It's exactly the same one as we have in the here's SF8 is a 1, not the SE8. Had a little mistake in there, but minus 1, 0, R, and 1. And so with this, I have shown you that we have produced a computer-generated set of equations, but also we produce the state space form automatically. All we have to do to complete this state space form is to get the output equations, but I didn't want to get too many things at once. But the A and B matrix first, and we'll deal in the next lecture with the output equations, just to complete the explanation. But the idea that I want you to see is that you have the computer generated form of these equations in here, and that is in the matrix form. You also have them in the Cauchy form, and then is where we can use these equations also to produce block diagrams, although we don't need to do that, but it can be used for that purpose also. But the main thing in this case was to produce the state space form, which you see that it produced the matrices here.